Hey y'all, Data Guy here. And today I have another video, not really a series, but just kind of a topic I've been exploring lately, which is distributed systems, designing them, and then also just talking about concepts and issues that might even arise when you're dealing with distributed systems. And so today, what I have for you that I was exploring and I want to then share with the Data Guy followers out there is linearizability. And linearizability is a key concept in the realm of concurrent distributed computing, and really in the context of when you have distributed systems and also shared memory multiprocessors. And what linearizability provides is a strong consistency guarantee, ensuring that operations on shared data appear to occur atomically, so each individual operation occurs individually without depending on or influencing another. Obviously, if you're building on and adding additional operations, they are somewhat linked, but atomicity says, hey, each operation can only deal with that specific operation and also occur in a sequential order that respects the real-time ordering of those operations. So what I'm going to explore in this video is just the definition of linearizability, what makes a system linearizable, the reliance on linearizability, some of the benefits, some of the downsides, implementing them, how can you implement a linearizable system, and then also talk a little bit about the cost associated with achieving linearizability. So without further ado, let's get into it. So now, what actually is linearizability? And so this is a term that's also known as atomic consistency and is a correctness condition for concurrent objects. You can kind of see an example here where an object is said to be linearizable if operations appear to occur instantaneously at some point between their invocation and their response. And this point is called the linearization point. So the primary characteristic of this, of linearizability, is that it respects the real-time ordering of operations. If one operation is observed to happen before another, then the linearization of the first operation must occur before the linearization of the second. So in this case, the first read v1, where x equals 2, and then it's written down there and it goes down into x equals 3, has to occur before the read v2 operation occurs where x is equal to 3. So you can't have this read v1 operation actually occur after the first, after the read v2 operation. So just really, really strict consistency on when your operations are going to perform. And so essentially you always have to have, in linearized systems, if an operation is initiated before another, that first operation has to complete before that second operation can be allowed to complete. And this is really crucial. I mean, it sounds really like nitpicky, but it's really important in these kind of systems where, hey, if another user makes an action to a database, or let's say there's a cryptocurrency contract, for example, but an example of real world money where, hey, if I try to extract money from one pool of Bitcoin and someone else makes a transfer request before me, maybe I have faster internet. If the system isn't linearizable, then I can execute my operation before that first person, and then I therefore get to get the Bitcoin and he gets nothing. So you can see why this gets important when you have systems that really depend on operations being executed in the right order to make sure, hey, this doesn't run out before someone else, before the first person actually requested receives that good or data or whatever. So here I have an example of a linearized and a nonlinear system. To make a more direct comparison, you can see here in the linearized system, after the actions B0, B1, B2 are all invoked at the same time, they're then all completed in action 1 and then waited for the action statement of action 1 to be completed before ending the operation. In a nonlinear system, all these operations are triggered at the same time, but some of them are actually completed before others. So B0 and B1 operations are performed before B2, and therefore B2 is performing operations on data that's already been changed by B0 and B1, unlike in the linear system where all operations are transformed at the same time. So I say all that to talk about, hey, what makes a system linearizable? So to achieve linearizability, a system must ensure that every operation on a shared object can be mapped to a single point in time within its execution interval so that the operations appear to occur instantaneously and in a sequence that is consistent with the real-time order of operations. And said more simply, it's making sure that the sequence that is executed is a sequence that was entered into the operation. key components that can contribute to making a system linearizable there's really three of them. There's atomic operations. So operations must be atomic, meaning that they are indivisible and uninterruptible. And this can be achieved by using like really old school hardware primitives like compare and swap, or software techniques like locks. The second one is sequential consistency. So the system must maintain sequential consistency, where the result of any execution is the same as if the operations of all processors were executed in some sequential order, and the operations of each processor appear in the sequence in the order specified by the program. And then third, you have real-time order respect. So that's what I was talking about earlier, where linearizability requires that if operation A completes before another operation B starts, then operation A must appear before operation B within the sequence of operations. So linearizable systems have a few unique advantages over just regular serializable systems. Number one, simplified reasoning. So linearizable systems are easier to reason about because the operations appear to occur in a predictable order, similar to how single-threaded systems operates. This simplifies debugging and verification when you're going back and trying to track down operations or identify bugs or errors. Everything is in a very clear sequential order. The second is client transparency. Clients of a linearizable system can reason about the system's state as if they were interacting with a single coherent system, rather than a distributed one with potentially inconsistent views if you interact with the one node over the other. And then third, you have strong consistency guarantees. Linearizability guarantees strong consistency across all your operations, making it suitable for really critical applications where consistency is super paramount. So things like financial transactions, inventory management, database replication, all great examples where even having one piece of data out of sync can cause huge cascading issues. So those are three of the big reasons why people will want to implement linearizable systems. So now that we know what linearizable systems are and some of their advantages, there are a few different ways that you can implement linearizable systems. And the first is lock-based approaches. So one common approach is using locks to ensure mutual exclusion, which then makes operations atomic. And so you can do this by saying, hey, if an operation has started, that operation has to finish before any other operations can initiate. Unfortunately, this can also lead to performance bottlenecks and reduce scalability, which can be kind of an issue when you're dealing with large systems or systems that need to operate super fast. Another option is optimistic concurrency control. So techniques like transactional memory and software transaction memory allow optimistic concurrency control, where operations are executed speculatively and then validated at commit time to ensure consistency. Then third, we have consensus algorithms. And so this is where you're actually implementing external developed consensus algorithms like Paxos, like Raft, which can be used to ensure linearizability by agreeing on a single order of operations across multiple nodes and then distributing that order of operations command across all those different nodes. Then finally, we have quorum systems. So quorum-based replication techniques, which are commonly used in distributed databases, ensure operations are linearizable by requiring a majority of nodes to agree on each operation. Actually also similar to how cryptocurrency networks agree on operations, if you're interested in that topic at all. So pretty funny, distributed systems, no matter what kind they are, they all kind of share some of these common characteristics and some of the common approaches to solve the same problems, because at the end of the day, you're just trying to figure out how do we achieve the same replication state across all of these different nodes. So with all these great benefits, there are some costs. And so while linearizability provides great consistency guarantees, you're going to deal with a couple different downsides. The first one, and I've already mentioned it, is performance overheads. So achieving linearizability often requires additional coordination between different operations, which then also leads to increased latency and reduced throughput. And this is very evident in distributed systems where network communication can be a bottleneck. So if you're dealing with that, linearizable systems might be difficult for you. Other one is scalability limitations. So the coordination needed to maintain linearizability can limit the scalability of the actual system. And because you have a overhead that is only going to increase as the number of nodes increases, which is going to just become prohibitive at a certain amount of scale, but you need that because that's what the overhead is, what ensures a consistent order of operations. So it's kind of a chicken and the egg problem. And then you also have complexity in implementation. Implementing linearizable systems is pretty complex, requires careful planning to handle edge cases, failures, concurrent access patterns. You're going to have to deal with some difficulty there. And then also, and this kind of goes hand in hand with scalability limitations, but resource utilization. Ensuring linearizability may require more resources in that overhead, or even just additional memory for maintaining logs, or higher computational power for consensus algorithms. You can't do something without a cost in compute power, right? But in conclusion, linearizability is a crucial property for ensuring strong consistency in concurrent and distributed systems, simplifies reasoning about system behavior, and provides the illusion of atomic operations that occur in real-time order. And unfortunately, on the downside, though, benefits of linearizability come with significant costs in terms of performance, scalability, complexity, and resource utilization. So make sure you have a thorough understanding of those trade-offs before you go down the rabbit hole of implementing linearizability. So hope you've enjoyed this video, hope you learned something new, and hope you have a great rest of your day. Data Guy out.